Let's try something else, and this is going to be our attempt number 2. And just look at the, if I look at the form of the equation, so there's an h bar here, and then there's this thing. So we can always apply to this equation I h bar d by dt plus h, and assuming that the derivative operator with respect to time commutes with h, which it should, because h will have spatial derivatives, partial derivatives. If you apply it to this equation, what we get is minus h squared, the second derivative of psi with respect to time. And on the right-hand side, we are going to get h squared of psi. So let's consider h squared. So if we now use the relativistic energy expression in h squared, then this equation will give us a second order equation where on the right hand side now we have minus h squared c squared by 2m Laplacian acting on psi, and then we have m squared c to the power psi. So unlike the previous attempt, this is a relativistic invariant equation. In fact, by rescaling things a little bit, you can show that this thing over here and this thing over here, they combine to make the D'Alembert operator, the operator that we saw that allowed us to have a a relativistically invariant wave equation. So this is a very nice equation, and this equation has a name, and it's actually very important in quantum field theory. It's called the Klein-Gordon equation. So although this equation is named Klein-Gordon equation, who derived it, this equation was actually first found by Schrödinger. And Schrödinger didn't use it to formulate his quantum mechanics, and you might wonder why. That's because this equation has a problem. See that this equation is second order in time. Because it's second order in time, you can now derive, so you can derive like a continuity equation from it, and there will be some charge density. Suppose that the charge density is rho tilde, and then you will have a continuity equation where this the time derivative of rho tilde plus the divergence of some current, say S tilde, is 0. Now, if you work out what rho tilde is for the Klein-Gordon equation, you find that rho tilde is I h bar psi star del psi del t minus psi del t. There's a star here. So of course, rho tilde has to be real, and it is real. But because there's a derivative here, and there's a derivative here, and there's a minus sign, rho tilde is not necessarily positive definite. Because it's not positive definite, you cannot have a probabilistic interpretation of the Klein-Gordon equation. Thus, we see that the Klein-Gordon equation is consistent with relativity, but it is not consistent with quantum mechanics. However, when we study quantum field theory, we shall see that the Klein-Gordon equation does make sense as an operator equation, and therefore it has important applications in quantum field theory. So our attempt number 2 is also a failure.